Hello everyone and welcome to another episode of No Orientation Programming. I'm Joe and today we will hopefully finally get a connection, a mass connection to our local gaming server. Let's see if everything is working fine. Yeah, seems to be fine. Okay. I have the local gaming server still running, and as you can see, it seems that the telnet listening port already had 8,000 connections. At the moment we have 6 active connections. This means that a lot of bots are connecting and disconnecting all the time. We should be able to write something. Yes. Let's see. Okay. So this is working. Oh, I can test something. Hello, and yes, on telnet we have full control now. That's cool. One thing I want to fix immediately is that on telnet localhost 4000, if I go to settings and then the version history, then I should be able to go up and down with the page, up and down, and I should always have a version here, a version string here. Like next one is 071, 062. Next one should be 061, and this is, yes, this is a bug. I don't know what is happening here. If I press capital J, it's working as expected. But if I press page down, we go to game selecting instead of this. So this is strange. Let's see what is happening. Version history. Hey, grüß dich, hi, noch online. Have a nice look. Okay, so this is strange. This is strange. So we need to check what is happening. We are in what kind of yes. So home paging version history. Yes, we are in home page history. Yes, if had you already have any experiments with the VSL thingy? No, not yet. Not yet. I have to set up the Windows virtual machine again. So, in this area, we are, okay, we are ignoring J and K. Oh yes, this makes sense. Key jump. We could. Let's see. Key jump. What is key jump? History stop. Key jump. Key is up jump. Is K or page? Ah, okay, page. Oh, yes, that. No, yeah, yes. Key down. Okay, that's the error. So now this should be fixed. Yes. So let's see. Version history. Page down. Okay, page down is not working anymore. Page up is still working, but page down is not working. Okay, that's so strange. So, again. Page up and down is jumping 6, yes. Version history. Page down is doing nothing. Page up is working as expected. 1, 2, 1, 2. That's it. And page down is not working anymore. Okay, key jump. Okay, I want this thing to be fixed. Oh, come on. Fly, please go away. I want this to be fixed very quickly. Warning log. A, B, key down jump, C, and here A, O, B. Okay. Let's make it in this window. It's better. Okay. Key J. Capital J is key jump. Key jump, that makes sense, yes. Key down. Page down, key process A. Key process A, yes, that's this key process. We have reached A, and this means capital J. Page down is capital J. Key is down jump. This annoying fly. So, this was it, buddy. Okay. J and So J and page down is key down jump, that's fine. So we have key process A, but we have ignored J. This means key is down jump, that's correct, but key is disabled. The J key is disabled because of this ignore list. So this is fine. So we have the key jump. Yes. What is happening here? What's that? A function key is yes. Damn it. Okay, now I understand. I need the same like here. If not function stop. If key is page down, then J and yes. Yeah, whatever. As long as it's working, it's fine. Now everything should work as expected, hopefully. So, page down 2, page down 1, page down 2, page down 1, yes. Now it's working. Yes, that's fine. So, cool. Now we have fixed something, that's very fine. Let's see what we changed. Key jump. I can do something different. If not J, if key is not equal to J and key is not equal to K, perfect. And I will move this up here. Yes, whatever. I think it's good enough and the diff is better. Version history. Yes, that's fine. Yes, perfect. Resources. History. We have... How many times do I have to open this? I have to fix this VI bug, that's so annoying. Now it's opened correctly. I don't know why. Okay. Fix page up and down in history. Okay. Fix page up and down in history. Fine. So that's fixed. Perfect. Very cool. It should work in the licenses as well. Page down, page down, page down. Yes, perfect. Oh, I love it. Because now that everything is working like in SSH, in the SSH channel. Okay, we have fixed something already. That's cool. So now, no, stop. Okay. The testing server. Okay, so the testing server is running. What do we want? An interval of 1000, that's fine, but we want 80 connections. But these 80 connections take a lot of time and we don't know why. So let's make one connection. And let's check this in Wireshark. Loopback and then port 4000. Yes, I think that's it. And then we connect. Start. Yes, that's it now. Stop. Okay, TCP. This is how it should look like. We have, let's check what TCP is doing. TCP. Transmission Control Protocol, that's what we want. Do we have, yes, and connection establishment, connection termination. I would like to have this as establishment. Okay. SYN, the active open is performed by the client sending a SYN to the server. The client sets the segment sequence number to a random value A. SYN sequence 0. From client to server. Then SYN ACK. In response, the server replies with a SYN ACK. The acknowledgement number is set to 1 more than the received sequence number A+1, and the sequence number that the server chooses for the packet is another random number B. Oh. And the sequence number that the server chooses for the packet is another random number B. Okay, the random number 1, A is 0, and then random number B is 0 as well. And this is A+1. Okay. Finally, the client sends an ACK back to the server. The sequence number is set to the received acknowledgement value. a plus 1, this is a plus 1, and the acknowledged number is set to 1 more than the received sequence number b1. Okay, that's a1 and that's b1, b plus 1, a plus 1, b plus 1, that's a plus 1, a plus 1, b plus 1, and that's b. Okay, so this is the whole connection stuff, and this is where the data begins. Data 1 byte R. Okay, we received an R. Does this make sense? I don't know. I don't know. Maybe. Okay. So, but how can we check only the first connection? How can we disable? I don't want to see. Okay, push is set. And not tcp.push. Flags push is equal to 1. Oh yes, this looks fine. This looks fine to me. Okay. And not tcp dot arg and tcp dot arg is smaller than 2. Ha, that's cool. This means I can remove this. I should get the same result. Ah, damn it. Okay, so here we only have one connection. Let's see what's happening if we do this again with the filter with 2 connections. Okay, this is not working. Ah, this is not working. Come on. So then we do something else. That is the testing process. Testing should not send anything. At all. So we again try to connect. That's strange. That's strange because we should not get any. We should not get any frame. Or should we? Let's make one connection again. So this is one connection. We get the syn from the client, syn arg from the server. Acknowledged from the client. What is this? This is from the server. This is from the server. This comes from the server, and this is the title, the terminal title, I guess. Telnet filtering. That's the title. And okay, and some stuff. Okay. That is FF. Let's see, the transmission protocol, options, payload. That's the payload. Okay. So this is the TCP payload, and we have FF, FB1, FFB3, FFFC22, FFFC22, 1B, 5B. Yes, that's the exit thing. That's 1B. 1B is the escape character. That's octal 33 is 1B, and then 5B, this is that one. Question mark 25 L. Then again escape 1B. Then 2 Naegulus. So and TO, yes, okay. TO and 07 is what is this? /A. What is /A? Okay. This is the window title, Bell. Escape. Okay, 2. The escape codes are so strange. Okay. Let me check. I got that. Here we have the A. What is 0 and what is 2? Why 0? What is the difference between 0 and 2? That seems to be Bell. The escape code in ANSI format is I want to see the difference. Where is the difference? Okay, whatever. Let's see what's happening if I use putty, wine putty. If I connect to no, localhost 4000 telnet. Title seems to be working. Okay. Whatever. As long as it's working. So we have a connection. So again, let's test one connection from the test server. Stop it. Okay, we have one connection, fine. So we have, yes, syn arc from the client. Then we have from the server the settings. We have an acknowledge from the client. Again, we have a frame from this from the server. But we have the server list already. Why? Because we are connecting from localhost telnet, localhost 4000. Okay, I'm immediately connected because gamer interacting means local connection. If connection local, then we have a specific data settings. We have a specific, we have the admin role and the login is done. And we don't have intro start. Yes, guest introducing. Welcome, quit. Okay, so this seems to be fine. Now this exact sequence must be visible in for 10 connections. That's fine. Let's make 10 connections. Yes, seems to be fine. So, okay, here we have a TCP retransmission. Why? The server tells us we have only 8 connections at the moment. No connections are pending. We have created 31 connections. We should switch to a different port so it's silent for us. And we only see TgsTesting 4002. And here we want to see only TCP port 4002. Okay, so let's do it again. We have 10 connections. Fine. Let's start these 10 connections. Okay, 10. The testing server thinks we have 10, and the server only sees 8, and we see retransmissions here. Why? What is happening? Okay. This thing believes that it is connected. No, what exactly is connection count? Connection count is, yes, as soon as we are ready, send ready, and send ready is TCP transferring ready. Send ready is true in case of what do we get here? We only get 0 if return value. If the connection or binding succeeds, 0 is returned. What is happening here? We still have only 8 connections. This thing believes that we have 10 connections. Let's see. We need to check how many file descriptors are open. Yes, that's what we do. Gamers 0, 0 created, 0 active. Okay, fine. Now we have to check testing. We go into the folder of the process. That is yes. Then we have FD. Yes, okay. Now let's try to understand what these numbers mean. What is FD info? That's cool. Mount ID flags. Okay, FD is better in that way that we know. Okay, we have three pipes, standard input, standard output, and standard error. Then we have 3 sockets open because of the debugging system. That is 1, 2, 3. I think 3 or 4. 3 or 4. How can we check this? Yes, list of open file descriptors, yes. LinkedIn. I've never seen a post in LinkedIn. Okay, yes, file descriptor, that's fine. But we only see it's a tool that shows all open files on the system. If no, okay, let's see what this thing is doing. LSOF process, yes, that's a cool tool, I think. List open files of process. Yes, that's better. Yeah, absolutely. Because now I can check what the hell is that. Ugh. Wow, that's interesting. Okay. Type. I want to filter LSOF. I only want to see select IP46 files. Okay, let's see if this is working. No. LSOF IP list only IP. IP4. What the hell? Oh, okay. No, I just want for this process. Oh, come on. And then yes, let's grab TCP, whatever. Let's make it cheap and easy. Okay, so now we can see. So this is a good overview. Okay. The debugging server is at 2021-22. What's that? That's the command line interface. Yes, that's the command line interface listener. That is the connection that is currently open to the command interface, and that's the open connection to the process tree of the testing application. Okay, now if the server tells us no connection present, the testing application tells us no connection present. Now we restart the connections. This thing is now this thing tells me now that we have 10 connections open and finished. The server tells me only 8 connections finished. Let's see what is happening here. We have 6 open connections and now we should have 16. Okay. And let's grab 4002. Then we should see how many open connections we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So actually the testing application we can count it in a different way. A word count, L for line numbers, 10 connections. So even list open files tells us that 10 connections are open. That's it. And in the trace we should see let's make a cut delimiter field 2 and then let's make a sort. I want to see all of these. I want to see the message of the server with the length. We can use the length. TCP, there must be a length somewhere. And TCP len is bigger than 100. Oh yes, that's fine. That's cool. Now we should have 10 times this message. 1, 2, 3, 4, 5, 6, 7, 8. That's interesting. That is a bad idea because yes, it emphasizes this situation that the server thinks we have 8 connections. That's true. That's the reason why we only get. Interesting. Very interesting. Okay. So actually I think the gaming server is doing something strange. Do we lose some connection? Port numbers reused. Okay, let's see what is happening. Okay. We have a lot of connections. Let's copy these and localhost, yes. Testing temp. Fine. So let's, yeah, that's okay. So again, I want to know what it's not what I wanted. Yes, that's one. That's the one. So we have seen 18. 18 is fine. We saw 18. We saw 28. We saw 30. We saw 36. We did not see this one. We saw We did not see this one. We should see the rest. 5970, 5986, 5994, 51010. So these two connections, not okay. These are okay. For whatever reason, I don't know. So let's check what is happening, and TCP port is equal to okay, let's see what this thing is about. The client from port 5944 is sending a SYN packet. Then we have a new TCP session is started with the same port as earlier session in this trace. Why? This frame is a suspected retransmission. Why? Because we have sequence 0, second SYN packet with sequence 0 from the same port. Yes, okay, and then the server sends okay, as expected, to this port, and okay. I think the server should see that the connection has been finished. What do we see here? Okay, we have a lot of retransmissions. That's okay, but all the other ones are getting okay. This is a not working connection. The other ones, all the other ones get a connection. Get a frame. They get a main frame like this one. A frame like this. And the same port, this one, 51010 gets the title and gets the main the server list frame. So for every connection, we should see two frames. 50994 title, 50994 main frame. 15986 title, 15986 frame. But only this one. The other frames are sent here. 5928 title, 5928 frame. But only for these two, we don't get We don't get a frame. Okay. Not getting a frame means TCP, let's check from the beginning. Yes, let's check from the beginning. Got file descriptor, yes. But I don't, I not only want to see the file descriptor, but I want to see the address. Sin address from the TCP transferring thing. File descriptor. That's server start. Yes. Socket option set. Address info set. Okay. Get socket name. String and port. TCP transferring. Come on, open this thing correctly. That's so annoying. What the hell? I have to change this as soon as possible. Address local is not here. Yes, as expected. It's in the transferring state. Yes, now I have to open it 10 times again. Address local. No, the remote. I want the remote, I think. Yes, this one. Socket file descriptor. Now I'm confused. I'm get peer name. Okay, get peer name. Yes, of course. Okay. So let's do this for the listening part. Got socket file descriptor, fine, but I want to see something else. I want to see this. I don't need the socket name. But I want to see this. String. Address remote and port remote. That's fine. Address LAN, fine. We have a buffer. That's fine. Okay. And here we say got peer. And we say no. Hopefully this is working. C string. Network to string port. Network to host short. Network to host short is then this should be something else. uint 16 type, I think. Yes, that's a buffer string of the buffer. Okay, but let's make it simpler. That's better. This does not have a C string. That's stupid. Okay, we don't need this, so we don't need this. And we can replace this. No, it's ugly. So I think that's it. That's good enough, hopefully. So TCP listening. The server. The shadows the previous local. What? Previous local? What the hell? Yes. Whatever. Was not declared in the scope. Yeah, of course. Because we have a peer socket file descriptor and we want a peer name. Okay, finally. So we have 0 gamers and 0 connections. We recompile this thing as well. Got peer at That's fine, that's cool. So now again, we have to TCP. Okay, I have to make a script. Con show. Okay, bin sh, and that's the PID of whatever. And that is ps minus PID of TGS testing. Is this? Oh, that's working. That's fine. And then we have lsof process p con show. Yes, but we want to grab TCP. That's fine. Now we have the TCP connections of this testing server. Con show. Yes, perfect. We only have 6 at the moment, as expected. Now we have our server. Server still running, hopefully. We want to have how many? 10 connections. And we start the action. Yes, this thing tells us 10 connections. We see 8 connections on the server, and we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 established connections. And as before, for some we don't see Yes. And now we should, yes, that's fine. Okay, listening socket has data. Okay. Oh, that's interesting. So this is our log. Okay. Let's see. This is our log. Let's open temp again. And we should see these connections. Can we remove some? Yes, we can remove some columns. Yes. Okay. Listening socket has data multiple times. We have, yes, adding visitor 8 times. Continuing the server selection 8 times. Yes. That seems to be interesting. Okay, so, but now, how many connections do we see? The same, we got. Okay, we can remove this as well. Perfect, adding visitor, process, yes, okay. We can remove these as well. Okay, good enough. What do we see? Which one do we see? We see 56. Yes. 10 connections. 1 to 10, fine. But now we could rearrange that. Should we rearrange the log? I don't know. But I can say listening socket has data can be removed. So we see how many connections. Yes, that's continuing to server selection. Okay. Okay, 8 connections. We see 8 connections, and therefore we only create 8 visitors. So that makes sense. Yeah. That makes sense. So why do we see 8 connections only? We lose connections. And this means in the listening process, we lose connections. That's bad. Okay. That's it. Bring a beer. We are coming closer and closer. I think we get an error, somehow we get an error, and this error is misinterpreted, I think. I think we have a misinterpreted error, something, and therefore losing connections. Okay, let's see. Listening socket has data. Let's see how many times I think I have only deleted 7 lines. Got P. Yes, poo again. Listening socket has data. Got peer, adding visitor, continuing. Mm-hmm. 8 times. Eight times. So even the select, oh, maybe it's because of the select. Ah, yeah, maybe. Why do we have a select listening file descriptor? Connect accept, because the accept is blocking. Accept is blocking. TCP server client example. Why do we have accept? Yes, this makes sense. Accept socket file descriptor used with connection based socket types. It extracts the first connection request on the blah blah blah. The first connection request on the queue of pending connections for the listening socket creates a new connected socket and returns a new file descriptor referring to that socket. So the connect is not interesting for us, but the accept. Oh, that's it maybe. We only have... Yes. Okay. For non-blocking you and domain sockets, the socket is... Connection in progress. The socket is non-blocking and the connection cannot be completed immediately. Why are we using select in this case? This does not make any sense, does it? This does not make any sense, I think. Interrupted, positive. Do we have E interrupted here? E interrupted system call was interrupted by a signal that was caught. Okay, I don't think we need this. I don't think we need the select. Okay, then how should we? If not positive, then select failed. Only if the select failed. But then we don't need this anymore. I think that's completely unnecessary. Okay, so and not check, but connections accept. Accept. Is this correct? Accept, yes. And this thing should be void then, I think. Because we don't have yes, no. No. Void, let's make it void for one moment. No. No. As long as we get connections, we fill in the queue. Yeah, perfect. So, but we don't have file and file interval read file descriptors. Yes, that's fine. We can remove this and this and the whole select stuff. Con pending true. We don't need a time interval. We don't need an. We need a result, I think. Yes, we need a result because the return value of this thing is integer. Integer. Yes, the socket. So we don't need a result. We should just delete stuff. Otherwise the Windows thing is not working anymore. Connections accept. This takes a lot of time. I think this is the... Is this the problem? Yeah, maybe. Yes, I think this is it. This was the problem. The TC... Oh, no. Stop. Yep. Connections check. Connections check. Okay. Let's go back for a minute. Because I think the problem is that we are entering this. If we are getting a file descriptor. No, we are not removing the file descriptor. We are not removing the file descriptor. This was not the problem. Okay. Again. Yes. All of this. Doing the same work multiple times is fun. Okay, what should we do if the buffer is too big? We make something else. We get an accept. Shut down if while peer file descriptor is not empty. Shut down close socket. Oh yes. So accept connections accept if is full. If the queue is full, then we close the socket immediately. Proc warning log. Output could not accept. No. Connection dropped. Output queue full. And dropping connection. Yeah, similar. Connection. Okay, peer socket file descriptor. Yes. If this thing is full. Okay, con pending. This does not make any sense. We should remove this thing. Con pending. Listening socket has data. That's dropping connection. Got peer. Yes. I think that's it. This thing should be non-blocking, is it? Initialize. Listening file descriptor, blah blah blah. Set socket options, reuse. Bind, listen. Ah, damn it. Okay. File non-blocking set. Socket file descriptor. Socket option set. Okay. Whatever. Int string error. What? Okay. TCP listening. Process listen failed, and then we have the shutdown. Hopefully, do we have shutdown? Shutdown, yes. While if listening file descriptor is not an invalid socket, then close the socket. Okay, shutdown is fine. So I just can Yes, okay is Oh, I have to be careful now. Yes. Is this the same function? Yes. Perfect. File non-blocking set. Okay. Where is okay defined? Okay is defined here. If defined when it's used, so we don't need this anymore because we have used it here. File non-blocking set. The listening file descriptor is non-blocking. If not okay, then could not set non-blocking mode. Yes. 2, 4, whatever. 1, 2, 4, 5, 6. 1, 2, 3. Listen failed and then non-blocking set failed. Okay, this thing should work out of the box still. Except address length, socket peer file descriptor, dropping connection, output queue full. We should at least we should in any case if except failed, yes, that's okay. Now we see, I think we see everything. Okay. Oh, except failed. Why? Yes, because now we have to check the stuff. Okay, fine. Except failed. Return pending. Okay, return pending. Positive is here. Dropping connection, output queue full. Dropping connection, output queue full means that we have received something and we should keep okay, I think that's the best choice here. Except failed, what does this mean? We should check the error number. Not only the error number, we should get errors. -1 is returned, and error now is set to indicate the error. Okay. Okay, let's see what is happening. 11. Okay, we have 11. Error numbers Linux 11. Maybe A in progress or something. E again. Okay. TCP transferring. Connect. Come on. So we have E again. Would block. Is this the same in connect and accept? Accept. Okay. We have these 4. If connect is this one. Would block and in progress. Okay. Windows accept C. Accept function. We should definitely check what's happening here. We get a socket from the accept. Okay. Return value. A value of invalid socket is returned, and the specific error can be retrieved by calling WSR get last error. Error get. Very important. Number error. So we need this as well. Yes. If invalid socket. Then get the error. Again, if peer socket is invalid socket, then no, let's keep it that way. In this case, everything is different. Okay, I think we can just copy this and we can say number error is error get. This function is defined, I guess, in the, of course, in the TCP listening and transferring int error. Yes, this one. TCP listening error get. If this thing hopefully has would block, the socket is marked as non-blocking and no connections are present to be accepted. Yeah. A in progress. A blocking Windows socket call is in progress or the service provider is still processing a callback function. Okay. A successful visitor must be called before this function. Okay. An incoming connection was indicated but subsequently terminated by the remote peer prior to the accepting call. By the peer prior to accepting the call. Okay, fine. Progress in file in a down network system has failed whatever, not socket is not a socket. Okay, so this is fine, I think. Except failed with error number and number error, that's cool. And here we should do the same. Not use error number, that's not good. Win32. We should not do this in any case. TCP transferring, error number. Only at this point. Otherwise we always have get error. Okay, okay. In listening, in TCP listening, we have error number and we should. We have this error number here. Int error number. Num error. Yes, is equal to 0. That's perfect. If we have a problem here, then no. I think it's okay to do this. Error number. Here we can reuse it, number error. Yes, because we have the number already in a variable. Stop. Number error. So here we have error get. The same. Perfect. Moin Productions, hi. What's up? What's up, Meister? One moment. Productions, is it okay if I speak in English? You can write in German if you want. The cycle times are not in nanoseconds, but we have a different, very strange behavior. The cycle times are at this in this region, 20 microseconds, I think, but where we have an even bigger problem. That is, we have our testing software which is creating 10 connections, and we see that in the network trace we see that all 10 connections are finished, and also the testing application thinks the connection is established, and we even check the Linux information of the testing application. We have on Linux we have an application that is called list open files, and we can provide the process ID of something, and in this case we use PID of TGS testing, our testing application, and then we see all the open stuff. We see that we have a lot of shared objects open, and these are the TCP connections. These are the listeners, and we have a lot of established connections. Now the server is closed, so some of them are closed already. But this was the initial state, and as you can see, we have in the Linux tells us that we have 10 open connections, but our gaming server tells us that only 8 connections are recognized. So we have a problem in the listening process, and we are fixing that at the moment. So we have, yes, I think we have everything we need, because like in the TCP transferring process, if we make a call to connect, then we may get an error, and this error can be E again. If we use a non-blocking socket, then we have to check this. What do you mean with our wire? The bug itself, or how I am coding? Both make sense to say our wire. Okay, break statement not within loop or switch. Yes, that makes sense. The bug itself. Yeah, so if we have an E again, what does it mean? The connection accept. We have the process function. The process function is everywhere in our system. It's always looping, always the same function. And in this function, last time, maybe if you can remember, we optimized this process by skipping a lot of checks. We only check a few times, and then we try to really check what is going on. And here we say connections accept, and only if we receive a positive, that means we have achieved something, we got a connection, then we try again, and if we don't get any connection, then we make a little break. Interrupted. This interrupted is not used anymore, but let's keep it for a moment. If we get a connection, then we tell the system, okay, positive. Okay, so let's see if this is okay. And if we have these errors, then we have to return pending because nothing happened. And if we had an error, then yes, we say pending as well. Okay, but only if we have another error, an error different than these errors, then we have a real error. This is just let's try it again error. So this is in fact this is no error case. The function itself tells us that it's not working because we don't have any connection, and we have to treat this as not an error. And this function may tell us there is an error, but a real error. So it's this function is a very old function from the very old C interface. So that's why it's very strange. So let's try it again. So fine, we can connect. That's a good sign, because this process is affecting all applications, and the first impression looks fine. That's cool. Here you can see the log of the official server if you're interested. Sometimes I see all the bots connecting. It's very interesting. Here we see all the bots connecting through Telnet and through SSH, and as you can see, they try to the bots try to break into the system by using the root password, and as password they have Ubuntu 1234. That's very funny. Or root and Ubuntu 123 and all the stuff. Root and password 1111. So this is kind of funny to see. Root password admin 123. So I can admin 1234. No, the bots are actually real bots from the outside world. Root and password 1. So that's real communication from the outside. If you turn on the SSH service on your PC, then these bots try to break into your system. As soon as you have connected to the internet and an open SSH server, they try to break into the system. Root password test. I will make a list. So this is a very good root password 1Q2. That's interesting. Cool. I have never seen that. 1Q 2W 3E 4R 5T. That's an interesting password. That's kind of clever. So this is a good example how we could set a specific connection to the blacklist. This is one thing I will do in the near future. I think that this one I will do in the near future, maybe in the next streams, because if somebody is connecting to the gaming server through SSH and is using root as the username, then this is invalid in our system in any case. So I can, this is very cool, because if a bot tries to log in as root, I can immediately set the IP to the blocked IP list, and then I have all the bots, a lot of bots filtered already, and it's affecting no user, and that's the cool thing. If we make a filter, then we should always make it in such a way that we always get the bots and the users should be unaffected all the time. So this is a cool example how we can filter the bots. That will be funny. Kicking all the bots out. So now again we try to as you can see, we say I have this command. I used this command. I have created a short shell script called connection show for the testing application, and here we say all the listening. These are the four listening, the servers, the four TCP servers in the testing application. In the testing application we have our our process view and our command interface. These two connections are the process view and the the command interpreter, and these are the listeners, the servers. And now we see in our gaming server we have 0 connections. In the local gaming server, 0 connections. And the testing application as well tells us no connections, and we try to have 10 connections. And let's see what's happening now. So this thing tells us again we have 10 connections in the server. That's strange. Okay, that's very strange. Now it's interesting. Okay, because that's bad. That's interesting. Okay, and let's clean up this code a little bit. So this is what we got from the log, from the gaming server. We see this stuff. Let's make, we don't need any process IDs, I think, at the moment. Okay, this is our log. And the Linux system tells us that we have these 10 connections established to port 4002. So we should see 10. These are 10 connections, 5 here and 5 here, and we should see 10 connections in the log. But we see 8, and I don't know why. Adding process 3, okay, that is something that is the system, the connection to the system debugger. That is not what we want to see, but here we can see that the TCP listening process gets the connection from 26, 28, 32, 44. Yeah, wait, okay. Then we get 400, 300, interesting. The last one. Oh, that's some queue. Oh, that's the behavior of a queue. Cool. Oh, that's interesting. You see? We lost these two in the middle. I think it's an overflow in the queue, in the Linux queue. Because we can read it like that. We have the first connection, 26. The server sees this connection, okay, fine. And these connections come in very quickly. And we see that we are processing four different connections, 26, 28, up to 44, and then we are we got one cycle, and then we are going out of the listening process. We are oh, come on, we are processing multiple connections, but then we go out of the process, and the main process, the message dispatcher, the main process, the management process, is creating the user interacting processes, the high level representation of the connection, and sending the welcome frames for these 4 connections, and then again we go to the listening process and check if we have another connections, but here we say that at first we process this connection. As you can see here, we have an ascending number. Every connection gets a higher number, 26, 28, 32, 44, and this should be the same in the trace. For example, the first connection in the time perspective is we received 26, 28. We have to check the SYN packets. And TCP flags SYN flags is equal to, is this possible? Flags SYN. No, this is not a good filter. TCP SYN is equal to 1. That's okay. So, but SYN only, and let's see, and TCP flags ACK is equal to 0, then we should see only the connection attempts. And here we say that, yes, here we see the connection attempts. If you have a TCP packet with only SYN from the client, then this is the connection beginning, the TCP connection beginning. And here we can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And as you can see, the numbers are growing. 26, and it takes just a fraction of time for the next connection. So we, as you can see, we get, this is in seconds, and this is milliseconds. So here we have milliseconds. In all 10 connections are done in 1/10 of a millisecond. And this, you can say it's almost immediately. But still, we have a certain sequence. Come on. So the sequence is always increasing numbers: 26, 28, 32, 44, 56, 58, 66, 82, 88, and 400. And this is the same sequence, but it seems that our server is processing the first 4 correctly, but then other connections are received from 56 to 400, and it seems that we have a limited queue in the kernel. This means we are losing the connection somehow. Because here we have an increasing number, the first one, the second one, the third one, and the fourth one. But here we have an inverted sequence number, because here we are reading a queue from the kernel. When we do an accept and we have multiple connections, then it seems that we always get the last one. And so at first we go this direction, and then we stop internally and do some stuff, and then we have received all these connections, and then if we check again, then we always get the last one. If we get one connection, then this is the last one, and we are moving this connection from the kernel buffer to our internal queue, and then we get the next connection doing the same. Get the next connection, we tell the server we want the last connection, we get this connection and we get this connection, but it seems that when we check again, this connection was not received already, so we are breaking. We are not checking for any other connections because we think we are done, and then we do process these for connections. But then these connections arrive at the kernel, at the kernel buffer, and then if we try to move from the kernel buffer to our internal queue, then we always get the last one, and that's 400, 388, 82, and then 366. And it seems that the kernel has dropped these two. So I have to check how I can increase this buffer. Listening socket buffer set C, whatever. Setting buffer size of accepted sockets. Buffer size of an accepted socket under Linux. The option would be to call that socket up and the newly created socket. However, TCP. What do you think? There is only one thing you can drink if you do socket programming. I should drink schnapps, not beer. Because this code is quite old. This code is quite old already. The file was created in May 2019. That was pre-COVID era. So it's quite old, and still I'm changing stuff inside this file. I only want a TCP connection. That's the only thing I want. But strange, it's still not working. Okay, that first quotation only applies to the receive buffer, and the real reason is so that the window scale can be negotiated. During the connect handshake, it is if it is bigger than 65K. The answer is indeed to set it on the listening socket, from where it will inherit by all accepted sockets, and no, it isn't the file status flag. Because on the newly created, so you have the TCP man. Okay, this guy wants to, this person wants to set the receive buffer size of an already accepted socket. That means this means we have two sockets. We have two circuits. This is the listening file descriptor socket. Listening socket file descriptor. It's the listening socket file descriptor, and that's the if we this is where we listen, and if we accept this thing, if we accept a connection on this thing, on this socket, then we have the peer socket file descriptor. And this person wants to set the receive buffer of this socket as well. Has, if you send a data to this socket, then this socket has a receive buffer in the Linux kernel as well. And if we make a read and we get bytes, then we get bytes from this buffer, from the Linux kernel buffer. And we have moved the data from the kernel space in the Linux kernel buffer to our user space in our application. Then we have the data in our application. That's how it's working. Holy moly, what is happening? And this person asks, not what we want. Increase buffer size of increase listening socket buffer. How to create this a certain socket? Listening accept missing connections. C. Let's think about what is happening. What is happening? A TCP handshake. Okay, wait. The accept system call is used with connection-based socket types like TCP pack. This is TCP. Socket stream is TCP. It extracts the first connection request on the queue of pending connections for the listening socket. Socket file descriptor. This one. Creates a new connected socket and returns a new file descriptor referring to that socket. The newly created socket is not in the listening state. Yes, the original socket is unaffected by this call. Okay. The argument is a socket that has been created with socket bind and listen. Okay. The argument is a pointer to a socket structure. This time. As known for the communications layer. Oh, okay. Oh, one moment. We can simplify something. I think that is we already have an address and address length. Yes. So we don't need this. Oh, we don't need these. We don't need this variable. Address length should be okay, I think. Address address and again, yeah, hopefully this is compiling. Oh, I did something I didn't want to do. Okay, bad. Okay, whatever, we check, we save this log, server.log. Uh, 16 megabyte. And then we can check what the bots were doing the last days. Okay. I wanted to restart the local server. Still compiling. Seems to be fine. Okay. Oh, Reinventor. Reinventor is raiding. Hi. What's up? Hi Reinventor, how are you doing? For everyone who doesn't know Reinventor, a shout out. Cool guy. He is coding in Rust very often. Yes, today an English stream, but you can write in German, of course, no problem. We have some strange behavior, of course, because we are coding in C++, and in C++ you very often have strange behavior. We are trying to code a testing application for our server that is making a lot of connections. For example, we have our server running, and we want to have we want to see how many connections we can make until the server is slowing down. Because the way we are creating our system is strange somehow, because we are not using the select function. We are always polling everything, and but today I have something in whatever. And it's not the usual way how you do it, but we want to check how many connections we can process. And we have a very strange behavior, because we are checking in the network trace how many connections are established, and we try to create 10 connections simultaneously, immediately, in parallel. And as you can see, we have in our server, the local server tells us 0 connections, and the testing application tells us again 0 connections. And these are the open file descriptors of the testing application. This is the debugging service. And these are the connections for the debugging service. So 0 connections to the gaming server. But if we start 10 connections, let's make this, and then we start 10 connections. Then the testing application tells us we have 10 connections, but the gaming server tells us only 8 connections were created. I don't know why. I don't know why. And you see in the trace that 10 connection attempts were made very quickly, in a very short time, but yes, 10 connections, and they are finished, because the Linux system of the test tells us, the Linux kernel tells us that now we have 10 established connections for the testing application. And that's kind of strange. That's quite strange, because the only thing I can imagine is that I simplify the log a little bit. The only thing I can imagine is that we have that the Linux kernel is dropping the connections. I'm curious if we have the same behavior now. All the connection file descriptors have an ascending number. The number increases every time. 688, 696, 700, 6, 18, 26, 32, and so on. And here we should see again, yes, we have the same behavior, I think. The first connections are processed immediately. 88, 96, 06, 18. And then we are stopping. We always have a polling mechanism, and this polling mechanism checks all the time if are there any connections we have to process. And we get a bunch of connections all the time. And in this case, we get 4 connections. And then we do stuff. We create our processes, our high level processes internally that are associated with the connection. As you can see, adding visitor and creating a gamer interacting process, which is sending the frames. And then we return again to the listening process, checking again, did we receive any new connections? And then we see something strange, because then we get the last connection, this one, and then we get the connection before the last one, and then so on. And it seems that it is always the same, that we lose the 2 connections in the middle. So I think the listening the kernel buffer of the listening socket has an overflow, and the kernel is dropping the old connections, I think. Maybe. I guess. Because we don't get any other error of the accept call. One thing I want to show you, guys, it's very interesting. On Arch it would never happen. Reinventor, yes. Of course it would not happen. This is the log. This is the log of the main server, which you can reach on Nigelus. Telnet Nigelus USTO. This is the main server. And if you connect, then I see this in the log. And the cool thing is, there are already bots trying to connect to the server, to the SSH part. And they are trying, of course, they try to log in as root. And they use a lot of interesting passwords, like root password is Ubuntu 1234, or they are using Ubuntu 123 and 1111 and so on. It's very cool. Root 12345. And this will be one criteria in the future. If someone tries to connect as root on the SSH side, then I will block the IP immediately, because then I know it's a bot. So this will I'm quite excited when I'm implementing this filter. No, I'm not using fail to ban, but it would be interesting, yeah. Yeah, yes, I have to remove this. This log entry of in any case, the SSH transferring, I have to remove this because this is very bad. So I can't fail to ban, I think, is an application. Please correct me if I'm wrong, but I think it's a application that analyzes a log, and from the log it's banning IP addresses, setting the firewall accordingly. And yes, I can remove the password, of course, and I can filter on the access requested. If I have an access requested message, user root, then I could filter this, but this will be done completely internal in the application. So in the application I will have a centralized a static function, and no matter where in the system, if anyone detects a strange behavior on whichever layer, whatever layer, then I have a centralized function. I want to block this IP because on this date, on this time, because of and this will be implemented later. But I hope I'm right that I have a too small buffer or whatever, too small Linux buffer, because I see in the trace that every connection gets accepted, and I thought my testing application is wrong, because the testing application tells me that 10 connections are successfully connected, and now I see that all the Linux system as well sees that these connections are ready, but the gaming server tells me nope. But that's strange, because where are these connections then? Because they can't be. This sounds legit. Do you really have Arch on your system? I have a friend of mine also uses Arch. A friend of mine uses Arch, and I have been using it. I used it. I used it many years ago, but I tried to update it twice, and yes, I use Arch by the way, and I used Arch by the way, and 2 times I tried to update this thing, and then everything crashed all the time because I'm too stupid for it. I need some noob Linux distribution because I'm too stupid to do real Linux stuff. But I wonder, how can I change? not everyone is ready for it. That's true. I know that there is a function setting buffer size of sockets. You can set the buffer size of sockets. And this person is asking, what is the correct way to set buffer? For example, socket option receive buffer or send buffer, size of an accepted socket under Linux. The obvious answer would be to call set socket option on the newly created socket. However, the TCP man page states, on individual connections, the socket buffer size must be set prior to the listen or connect calls in order to have it take effect. That makes sense, as the buffer is likely allocated upon creation, and therefore I would have to rely on the inheritance semantics of the listening socket by setting its buffer size, except the man page, not that of the socket, makes any mention of the inheritance and actually states, on Linux, the new socket returned by accept does not inherit file status, for example, from the listening socket. So it seems to be a little bit different somehow. Whatever. Let's try doing something. And that is a socket. Maybe it's the socket buffer. Sets or gets the maximum socket receive buffer in bytes. The kernel doubles this value to allow space for bookkeeping overhead when it is set using set socket opt, and this doubled value is returned by get socket opt. The default value is set by the default file. And the maximum allowed value is set by the file. The minimum doubled value for this option is 256. Let's see what we have here. This is 200k. Is this correct? But this area max. But this can't be that big. What do we have in min? There is no such. Yeah, whatever. CD. What do we have here? Receive memory, default and max. I'm losing connections and I don't know why. That's the strange thing. Because at which point we have a TCP connection. A TCP connection is the creation of the connection is done like that. You have a SYN packet. It's not. I don't see that on the testing application side, on the client side. I see that the connection is fine. Everything is fine. But on the server side, I don't see that the connection existed. That's the strange thing. And the connection establishment is done like that. You have a SYN packet. You have three packets. The SYN from the client, then the SYN ACK from the server, and then the ACK from the client. A three-way handshake. A SYN from the client, then a SYN ACK from the server, and then an ACK from the client. And this is done for all the connections. Here we have retransmissions. But I checked, we have in this case 6 different retransmissions, and at least four of them are fine. So this is not. We have a lot of connections at the same time. We lost in this case 26, this one, we lost this one. And as you can see, these are the last ones, the last connections. The last connections. Yes, I think it's like that. It's like that. I think it's like that. If it's going like that, I think. If you have a client, a TCP client that is connecting to the server, then the connection is created in the Linux kernel as not accepted connection. Then it's in the kernel buffer, I think, in the listening socket, in the buffer for the listening socket. And as soon as I do an accept, then the server is sending the SYN ACK, I think. We only get the SYN ACK as soon as and this trace would say the same. That is, the server is checking for 4 connections. It's checking for connections, and it has got 4 connections. This one. A client tries to connect 688. We accept this connection, and because of that we send this synac. We moved this unaccepted connection from the Linux kernel to our user space application, and if we execute the accept function, then the Linux kernel tells the client that the connection has been transferred to the user space internally. So we have taken this connection, and the Linux kernel says yes to the client. Yes, I have transferred your connection request to the application, because the application has received this connection request because of the accept function. And then the client tells us, okay, fine. Then again, we have another connection attempts, 4 attempts, as we can see here. And after 4 attempts, we can see here in the trace very clearly, I think, we get 1 synac for 688 for this one. Then from the server, this is the server side, 4002. Then for the next connection, 96, we get another synac from the server. So a second connection has been accepted. And then again for 706, and then another one for 718. And after that we do stuff internally, because we are stopping accepting stuff because we are doing something else. And then we see, this is the last arc from the last client, and then we see these 6 connection attempts. That's it. I think that's how it's working. We have 6 more connection requests from client, 726 up to 768. Like here, these 2, but these 6 packets. But we are not accepting them yet. We do something else. We create the high-level processes, and we are communicating with the prior connections, with the 4 connections prior to that. And then we get the frames. That this is the title setting for 688, and then we have the frame. These are the frames for the first 4 connections. And then the clients, the 6 clients, are asking, hey, what's up? We try to connect. What's going on? And then later on we oh, that's cool. That's cool, because here we see in the trace oh, that's interesting. Now it's getting interesting, because now we see we have done the frames for the first 4 connections, and then we have accepted 1, 2, 3, 4, 5, 6. All of the according to the trace, to the network trace, we have accepted the 6 other ones, the 6 other connections, and beginning hopefully with 768, then 56, then 48, 46, that's correct. And yes. I think we are close. We are so close, and I think I will. The problem is here, I think. The problem is somewhere in between here. Yeah. I will do something like that. Haha. I will split this error. I will split the errors. And then we get what is happening. So that's... Ooh, I have to stop. That's... So. 4. So I check for every... every error. And I think E in progress, yes. We don't want E again. So we move this. Yeah, it is not Rust, you're right. Yes, it is not Rust. How is a connection created in Rust? Do you have an example page? There is an example page for C. So, except failed. E again should be fine. So let's do this. I think this is a good approach. So, oh no, stop. Oh, damn it. Didn't want to do that. Yeah. Now. Oh, damn it. Still not what I expected. Yes, only closing 4. Selected packets. Okay. I have a new issue in testing doc. Let's say now TGS doc issues 23 July 25. Move. No. Test 1 being to here. Okay. Very important. Oh, that's already in here. That's fine. Yes. Okay. good enough. So, okay. What I expected is that I get some other error. I thought that too many errors are filtered. That's not the case. And this can't be the problem either. Because if this is this is our internal file descriptor queue. This is our internal file descriptor queue, and if there is a problem here in the output queue, because the queue is 2, how big is the queue usually? I don't know. Max connection set, what is this? Max con. Yes. Okay, fine. But I think it's not used in the main dispatching process. Always there are some bugs that are very annoying and strange. That's the nature of bugs. So I'm struggling. I hope your stream was better. What did you do today? I will fix this problem today, no matter what. TCP transferring. Okay. We are not dropping any connections because of the queue, and telnet, MP telnet is we create the listening process here. That's the telnet process, and we are not making any constraints. So this means, what is the default size of the queue? Because the and from maxcon, yes, maxcon is 20. The size of the queue is okay. We don't have any restriction in the pipe. That makes sense, yeah. Core pipe. Size max set. Okay, size max. Pipe base. Default size max, okay. 1024. What did I do here? The hell? That is ugly. That is ugly, I think. Yes, size T. That's bad. Okay, so we say const size T. What? Okay. Let's okay. Okay. Don't never change a running system. Okay. So so I think we should not have any restrictions because, and nevertheless we should see this warning if something is wrong here, and we should see this thing if anything is wrong at this point. I don't see why we are missing these two connections all the time. These two in the middle. Something interesting happens in between here. Why only 4? Four connections. You know what? I don't care. I do this. Yes. Whatever. So that's correct. Now we have oh, yeah, that's bad, but okay, whatever. No, stop. Oh, so bad. Okay, again. Ah, fuck. Okay. Connection reset by peer. This was the process trip here. Okay. Yes, now. Ho, ho, ho. A perverted way how to do it, but let's see. Let's see what's happening. Close, wait. Yes, whatever. I think it's okay. At some point, these connections had the state established. Okay, now we have a lot of -1. Okay, so fine. Okay, we have oh, that's cool. That's cool. That's socket file descriptor 9. Oh, cool. We get socket file descriptor 9, 10, 11, 12. 9, 10, 11, 12. Oh. Yeah, now it's interesting. Oh. Oh, stop. So. 12. What? Peer socket file descriptor got peer. As long as it's... This is... that's interesting. Okay. Nah. We will fix it today, I think. Yes. As you can see, we try to check connections. We try to check connections. Then we get some connections. Now we don't get any other connection, and we do internal stuff because from outside we don't get any more connections. Then we're doing stuff, and then we got a file descriptor 13, and the Linux kernel tells us that the file descriptor 13 belongs to 680, but we think that it's 740. Hi, Folsen. Hi, Folsen. How are you? You're looking for a hacker, cool. No, I'm not a hacker. I'm not a hacker. I'm not even able to make 10 connections simultaneously. That's so strange. Why do we think that the file descriptor 13 is belonging to 740? That does not make any sense. I mean, theoretically the application can be multi-threaded, but it isn't multi-threaded at this point, so we can't have a problem with that get peer name function. Get peer name is init to p. That's also not a problem. Bruder, you know anything about shard? Can that be cracked? I don't know. I know I'm using shard 256, but I don't think it can be cracked. What is happening? What is happening? A man init to p. Yeah, let's check it. And man get peer name. But this can't be the problem because we get... Let's see it in a different way. We get 9, 10, 11, 12. 9, 10, 11, 12. I'm working on a gaming server. And this gaming server can be connected. You can connect to the gaming server with Telnet, Nigelus, USTO. If you know what Telnet is, Telnet is an application on the terminal. It can be used on Windows and Linux. If you connect to the server, then you have this interface. And then you can create a game like this, Connect for Gaming. And then you can move around and play with others. And what we are doing now is trying to... I know nothing about coding, bro. That's why I decided to ask you about this and that, if you know what I mean. Yes, I know what you mean, but I don't think it can be cracked somehow. So it's safe. That's the intention. I think. We got a peer. We got a socket. Should we do it again? Because... Yes, I do it again. I do it again. Because here we say B. That's the only thing I can think of. A. Yeah, now I do this because I want the testing server not to write out this mess. Okay. So now, perfect. Yes, perfect. Now, reset the network trace. Then again, we call this test 2. And we make another one, test 3. And doc issues. Okay. Okay, so now we should be able to see AAA. Yes, perfect. And I want to create 10 connections and I press start. And now I stop the server. Yes, I see something. Ah, that's bad. That's so strange. Okay. Whatever, let's see. I don't know what's happening here. Okay. So this is the server log. And this is, yes, fine. Don't want to be confused. So let's see. That's so strange. We have missed, I guess, these 2 connections. Yes, perfect. We get some stuff, then we process this stuff. 9 is 648. 9 9 is 600. Damn it, now it's even more confusing. Oh, come on. This is what I expected. 9 is 640. 10 is this one. 11 is this one. And 12 is this one. Come on. This was confusing, yes, but now it's even more confusing. But maybe this is the cause, the root cause of the bug, because this thing tells me exactly. Yes, here we have 3. Yes, that makes sense, because the first 0, 1, and 2 are the pipes, and then we, as soon as we create the listening process, we have 3, 4, 5, 6, 7, and so on. But this thing should be no. I have to be careful, because we have multiple listeners. Yes, we have multiple listeners. Yes, that's the problem in this case. I'm not allowed to remove the process ID, this process ID. That makes sense. That makes sense. Okay. More or less. More or less. Now, as you can see, it's even the same process ID. It's even the same process ID. It's the same listener. And the same listener tells me that it got a file descriptor 8. No. This is not. This can't be true. This is so strange. Let's do something else. Mem set. I can't believe this. This is not working. Oh, come on. Address. Let's make it a little bit better. Equals 0, and only then we get some information. Okay. I will find this bug. I will find this bug. Perfect. Fine. Perfect. We got 7 and 8 in this case. Yes, okay. And then we start. Fine. Okay, again. We have test 4. I will copy even these two, and I think we have lost these two. Yes, bug finding is very bad. Very boring. But with enough beer, it's fine. One moment. Cool. I did not know that. Hi, lazy. Oh, then you have found your hacker. Folsen. I don't want to break. Good evening, lazy. We are. You're not a hacker, but you, just a little dev. Yeah, I'm just a little dev too. I'm not even able to make 10 connections. I make 10 connections and 8 of them are working. It's so strange. I did not reset the trace again. Come on. I always forget to reset the trace. But here we say the same problem. I try to connect. I try to make 10 connections simultaneously, and it seems to be fine somehow. But we have some issue, of course, and that is that we try to make 10 connections and only 8 connections are yes 10. Oh, now I did something strange. One moment. Yes, I have a server. I have a server that has a listening. Is listening on a socket. The server is listening on the port 4002, and I have another application, a testing application that is creating 10 simultaneous connections, and it's telling me that it has achieved 10 connections. So, and I thought the testing application is lying, but actually I see that the Linux kernel tells me, yes, you have created 10 connections. Fine. Fine. And even the trace tells me that that we have created 4 connections. Then we tried to create another 6, but the server was not responding for the 6 because it was busy sending, creating stuff internally and sending the responses, the frames, and then all of the 6 connections tried a retransmission. They made the first packet of the three-way handshake of the TCP connection. So these are the 6, and then even in the trace I see that somehow I accepted 6. I accepted 6 connections, and then I sent, but I only sent, yes, and I only sent 4 4 frames. So internally I somehow I create 6 more connections, 10 in sum, and then I only get the frames for 4 connections because the server thinks, the gaming server thinks it only has 8 connections, and I don't know why, because I tried to make a log that is telling me I'm always executing the accept function on a non-blocking listening socket. So this non-blocking listening socket can have an error, except socket file, a peer socket file descriptor, and I can get an invalid socket, for example E again, because it's a non-blocking socket. If we don't have any connection, then we should get an error E again. That's okay. But I should see all the other connections. And in the log I see bugs are annoying. So let's check what is happening here. Yeah, bugs are really annoying. So now what is oh, this is so completely bad. My VI is broken. I don't know why. If VI is broken, then you have serious problems. If the VI is not working anymore, then you have problems. So now hopefully. What is wrong? I don't get it. Do you see that? Oh, come on. This is so again, one more time. Copy from X to console VI is also a problem for me. It sucks so hard. Yes, usually it was working. It was working in general. Maybe it's because of the color codes, I don't know. Now I make it so now I have saved it. I make a copy. So hopefully it's working now. Also on the video clipboard. I have compiled VI to be able to use the X clipboard. Now it seems to be working, hopefully. Cool. Yeah. Oh, yeah. It seems. Oh, now it seems to be fine. Okay, hopefully. So this thing is showing all the connections, the TCP connections of the testing application. The testing application itself has 3 TCP listeners for the every application has a debugging service. So I can connect to every application and see the process tree of every application. These are the first three listeners. Then I have the listener for the command terminal for the testing application. And this is this window for the testing application. Then I have the two connections. I connected to the command terminal and to the process tree. These two windows. So this is these are the connections for the testing application, and these connections are made from the testing application to the server, and the server is listening to 4002. And as you can see here, we have 8 connections. Why do we have 8 connections? Our TCP listening process, which one? Listening socket 7, yes, fine. Oh, we can do something else. We can check something else. We can do the same for the server. What is the server telling us? PID of TGS, PID of TGS, yes, that's fine. And then let's say ls list open file descriptors of process TGS, and then grab TCP. Cool. So this thing is ooh. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, come on. Okay, we have we have 3 listening ports. This is the debugging service, as we have here. These are the debugging listeners. And then I have 2 listeners. The first listener, this listener is the telnet listener, and then I have an SSH listener. Here you can connect with telnet, and here you can connect with SSH. And on the telnet side, oh come on, is this great? This is so crazy. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So the Linux kernel tells me, yes, you have accepted 9 connections. On the server side, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the client side. Stop. Oh, okay. Oh, now it's better. Okay, only these. Okay, then we have 8. That's fine. Yes. How is this possible? Because okay, let's see. Interesting. Okay, we have this is TGS testing You have tried to create the 10 listeners in a row with a small delay, maybe some race. Yeah, no, it's not 10 listeners, 10 connections. Yeah, okay. 10 connections. Have you tried to create 10 connections in a row with a small delay? Absolutely. The connections are apart only. This is the first one, the first connection. And as you can see, kind of immediately, I create 10 connections from here to here in a very, very short time. 10 connections in under 1 milliseconds. And there shouldn't be a race, I think, because everything in the application is in the same thread at the moment. So it's not a no multi-threading problem, because I'm not using threads at the moment because I don't need it. I think because if I get 10 connections, I process 4 connections and I do stuff, and then I process the other connections. So we get the answers for the first 4 connections in 10 milliseconds. And then we get the other answers, but okay, this is complete. Okay, one thing that confused me is solved, because I was in the last test I was confused because I saw this is the log of the server, and this is the output for the testing application, and the file descriptors of the testing application cannot be a match. Of course, that doesn't make any sense, but okay, let's check this one. So we have 8 connections. The connection number 8 has port 508. That's this one. These are the first ones. 508, 10, 26, 8, 10, 26, 42. And then we are doing something. Let's see, 8 is 508, 9 is 10, 10 is 26, 11 is 42. Fine, then we are doing something, and then we should see the other connections. 12 is, let's see, yes, haha, and that's it. That's okay. Now it's less confusing, because first I get all the connections in order. I created the connection for 508, 10, 26, 42, and then in between here some time has passed. Some time has passed because we are the server is busy at the moment. And then we on the client side we create 56, 60 and so on up to 606, but when the server has returned, then it's again processing the connections, and for the file descriptor 12 it got 606. Then for 13 it got 594, 82, and then 68. So fine, that's cool. That now it's less confusing. It's less confusing. So here we can clearly see what is more or less clearly see what's happening. And the client is sending 10 connections from here to here, these 10 connections. The server is busy meanwhile, and then the server is getting the last connections, and it seems that the connections in the middle are dropped somehow. So let me think because the trace tells me that we have 6 another synarchs. That means all the connections are lazy. Do you know that? Or nameless? Do you know at which time point I get the synarch? I think I get the synarch as soon as I have accepted the connection. I think when a client connects to a server, then the connection, the socket is put into in a queue of the kernel. A synarch should be in the handshake. Yes, genau. And I think as soon as a client is connecting to the server, then this connection is stored in the Linux kernel in a buffer in an unaccepted state, and then with the accept function I can move this connection from the kernel space in the unaccepted state to the user space, more or less, or change the state of the connection in the kernel to accepted, and copy and get a file descriptor. So if I do accept, I think the connection is moved from the unaccepted queue to the accepted queue, a file descriptor is created, and I get the file descriptor in the user space. That's, I think, what is happening. And as soon as the Linux kernel has moved the connection from the unaccepted queue to the accepted queue, then the Linux kernel is sending out this synarch as the connection is accepted. It would make sense because it would match exactly how the server is behaving in the logs. At first, accepting the first connections, the first 4 connections, what we see here, 1, 2, 3, 4. Then the client is sending 6 more requests, syn requests, as we see in the first 4. 1, 2, 3, 4, and then 6 another ones. But the server is not responding anymore because the server tells me in the logs it has accepted 4 connections and then doing something else, responding to the 4 connections, and then continuing receiving connections. And that's what we see here, sending the responses to the first connections and then accepting, according to the trace, 6 more. According to the network trace, I accept 6 connections. That's a strange bug. That's a strange bug again. And the kernel tells me on the client side, yes, you have 10 connections. And on the server side, it's telling me it has 8 connections. I don't even know how this is possible that I get a different result. So bad. I don't get any error. I have checked in the listening code is like that. We have a process function, and this process function is called every time, cyclically. And then we have a counter, so that is delaying the whole process. That's delaying the whole process. So it's lowering the cycle time, or increasing the cycle time. So we only do this every 100 cycles, whatever. But it has a cycle. And when we do this, we are accepting on a non-blocking socket. We are accepting on a non-blocking socket. So we may get a file descriptor, or we get an invalid socket. If we get an invalid socket, we may get the error E again because we don't get any connection. Linux, max unaccepted connections. TCP connection limit, there must be some limit. In local port range TCP fin timeout, there somewhere we have to look somewhere here. CD proxys. Yes, then we have net. I think the limit is pretty high as far as I know. Yes, I think. Is it core? I don't think that the unaccepted it can't be in the buffer, because the problem can't be in the buffer, because this thing is telling it this. Okay, let's remove this the parts that can't be the problem, because this thing is telling me it has 10 connections, and it's telling me the same as the trace. So the trace tells me we have created 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 connections. So according to the trace and to this thing, that's the content of the testing application. So here we have 10 connections as the trace tells us, same as the trace. Is it closed somehow? These are the we have a three-way handshake. Maybe the server is we have the three-way handshake is syn from the client. Client is this client port and then server port. The first client makes a syn, then the server responds with syn arg, yes, I have accepted the connection. And then the third one is the client acknowledges the connection a second time. So we always have a three-way handshake. 1, 2, 3. 1, 2, 3. 1, 2, 3. For 4 connections, we have the three-way handshake. And then we have 1, 2, 3, 4, 5, 6 connection requests and attempts from the client. 6 more requests, and then we do something, and then the server says, yes, okay, now I have time for you, and I have accepted all. I have accepted all of the connections. But then we need an acknowledge of the clients again. And do we get these these acknowledges? Oh, that's that's the first one. 2, 3, 4, 5, 6. Yes. Sequence 1, ACK1, sequence 1, ACK1. That's it. And yes, that's the server sequence. So we have 6. Yeah, we have the same. That's perfectly fine. 606, 594. And as you can see, in this log, the server is busy. The server is busy, and then we have 606. The server is responding to, is creating in the inverse order. 606, 94, 82, 68. And then, according to the log, nothing is happening anymore. Okay. Is it possible that we get in the accept function more than one? On success, the system calls returns a file descriptor for the accepted socket. A non-negative integer on error -1 is returned. Address len is unchanged. Socket address. This stretch is filled with the address of the peer socket as known for the communications layer. The exact format of the address returned with the socket's address family. So it's not a list like in get address info or something like that. There is a function called address info. Get address info man page. And here we can get a list of names, an address infrastructure. This is a linked list. If we have one name, for example www.google.com, then we may get the address of for the IP 4 version and the 6 version and stuff like that. But it's the accept function is not working like that. So if we get one file descriptor, then this is one connection. Okay, so the testing application is compliant with the network trace. And the server log is compliant with this output. The only thing that bothers me is how can this list and this list be different? The Linux kernel is telling me your testing application has 10 connections to this port. And the server application has only 8 connections. I thought this should match. Ah, one moment, I have to. Hallo? Hallo? Oh, why? Schaut's aus. One moment. Hallo, hallo? Hallo, hallo? Jetzt ist mich. Andi? Sehr gut. Geil. Bin nur am Streamen. Ich habe da einen schrägen Bug. Sonst ist am Freitag da? Jederzeit. Ja, wie es euch sagt. Also wir werden ziemlich 10, 12. Jetzt Mittag werden wir schon aktiv sein, glaube ich, und dann bis halt Open End. Und so könnt ihr eigentlich jederzeit vorbeischauen. Ja, geil. Ja, dann kommen wir bald schon. Kommen schon. Ja, passt. Ja, Ich versuche gerade am Gaming-Server 10 Verbindungen aufzubauen. Über Testapplikation. Und da versuche ich irgendwie 10 Verbindungen aufzubauen. Na, gar nicht. Wenn kein, okay. Na, passt ja, dann tue ich mal weiter streamen. Weil ich muss das halt noch fixen. Okay, passt. Ich wünsche dir was. Ciao. So, now let's think about what can be the reason. What can be the reason that we see different things here? I don't know exactly the time point when we get the synarg from the Linux kernel. I think it is as soon as we execute the accept function and we get a peer socket file descriptor. As soon as we get a socket file descriptor from the accept function, I think we send a synarg to the clients. But if this is the case, then I should see in the log 6 times that we got the peer socket. That's not the case. We see the first 4 ones and then the file descriptors are matching from the server side. So this is fine too. 12 is 606. 13 is 14. 15. So this is okay. This is okay. But we missed the old file descriptors. We missed the old file descriptors because of whatever reason. So one more test. No, yeah, that's the strange thing, because if we get an, if, for example, if we have four, connections, oh, yes, that's this line is not what I want. That's okay. Strange, but okay. Whatever. If we get an error, if we have four connections and then we get an error, then we should see this line. The accept failed because of one of these reasons. But we don't see this. We don't see this message, so we just don't see the connection at all. We don't see an error. We don't see an error. And we don't see the connection. Okay. Maybe hopefully somebody else has this, except dropping connections. Hopefully somebody else has this. Oh, yes. Close fin. TCP fin timeout, local port range, recycle default. What's that? Number of TCP IP connections. I'm programming a server and it seems like my number of connections is being limited since my bandwidth isn't being saturated. Even eliminate the maximum number of connections. This limit is are impacted by certain limits on both client and server sides. I'll bet a little differently. Okay, let's try to read the manual. On the client side, increase the ephemeral port range and decrease the fin timeout. To find out default values. To change values. Okay, port range. Okay. The ephemeral port range defines the maximum number of outbound sockets a host can create from a particular IP address. The fin timeout defines the minimum time these sockets will stay in time wait state. Unusable after being used once. Usual system defaults are. This basically means your system cannot consistently guarantee more than sockets per second. Yeah, as you say, nameless, the limit is pretty high. To change the values, The above should not be interpreted as the factors impacting the system capability for making outbound connections per second, but rather these factors affect the system's ability to handle concurrent connections in a sustainable manner for large periods of activity. Yeah, that's very well written. On a typical for recycle and reuse would be these do not allow a connection from a used socket in wait state and force the sockets to last to the complete time wait cycle. I recommend setting reuse and recycle. These do not allow a connection from a used socket in wait state and force the sockets to last the complete time wait. That's the reuse option we often set in the code. On the server side, the core somax.com value has an important role. It limits the maximum number of requests queued to a listen socket. If you are sure of your server application's capability, bump it up from default 128 to something like okay. Mm-hmm. 4096, okay. TXQLAN parameter of your internet card also have a role play. Default values are 1000 to bump them up to 5000 or even more if your systems can handle it. Bump up the values for netdev max backlog. $1000. TCP max syn backlog. This is interesting. TCP. Max syn backlog. Yes. And now remember genau, syn backlog. And so max con. Okay. Into the maximal number of remembered connection requests which have not received an acknowledgement from connecting client. The minimal value is 128 for low memory machines and it will increase in proportion to the memory of machine. If server suffers from overload, try increasing this number. Limit of socket listen backlog. Known in user space as somax.con, default to 128. See also the symbol for additional tuning for TCP sockets. Let's consider a TCP handshake, but one should be sure for your case. Yes, absolutely. Absolutely. So something else must be going on. Let's consider a TCP handshake. Let's understand what's going on. TCP max synlog backlog represents the maximum number of connections in syn receive queue. An example, when your server received syn, sent syn ACK, and haven't received ACK yet. This is a separate queue of so-called request sockets. Request sockets in code. Example, not fully fledged sockets. Request sockets occupy less memory. In this state, we can save some memory and not yet allocate the full socket because the full connection may not be at all in the future if ACK will not arrive. The value of this queue is affected by listens backlog argument. There is a listen backlog. Let's check this thing out. I think this is the problem. I think this is the problem. Hopefully. Come on, please. So, we have 0 connections. We make a clear network trace, and then we close this one. So now we recompile our testing application. Check this log. Okay, and then we create 10 connections. Oh yes. As always, the bug was in layer 8 of the ISO model. The bug is in between the chair and the and the screen. Or more precisely between the chair and the keyboard. So, okay, let's understand what is happening now. So, again, let's see what is the testing application telling me. Okay, 10 connections, fine. And now the server is also telling me I have, hopefully, 10 connections. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's read the man page, what I was doing here. What is the difference? Oh yeah. Okay, we can close all the stuff. Okay, man page of listen. That one. Okay. Listen marks the socket referred to by socket after we have created a socket, a listening socket with the function socket for TCP stuff. Then we have the socket option reuse address, that is if the socket is in the wait state, then we tell the Linux kernel no, there are no pending. Yeah, you can bind again. Even if it's in the wait state. Okay, so and then in the listen call you have a parameter, a second parameter, that is the backlog parameter, and that's the restriction you can make. Listen marks the socket referred to by socket as a passive socket, that is a socket that will be used to accept incoming connection request using accept. The socket FD argument is a file descriptor that refers to a socket of type socket stream or sequential packet. The backlog argument, and now it's interesting, the backlog argument defines the maximum length to which the queue of pending connection. Why do you read man online? Because I'm lazy. Because I don't know. Because it's here. On the left side, I could do man listen, yes. But now then I have problem with the chat. I guess this is the reason. But I'm not sure. The backlog argument defines the maximum length to which the queue of pending connections for socket FD may grow. If a connection request arrives when the queue is full, and we have to be careful because this number was at 3 and this is not, it's not the implementation behind listen is not required to use exactly the number you have provided. It can be more or less. That's bad. That's strange. In this case, I think it was 4, but that's strange. If a connect request arrives when the queue is full, the client may receive an error with an indication of connection refused, or if the underlying protocol supports retransmission, the request may be ignored so that the later reattempt at connection succeeds. So, what if we provide 0? What if we provide 0? If the backlog argument is greater than a value in here, behavior, nodes. To accept connections, the following steps are performed. A socket is created, the socket is bound to a local address so that other sockets may connect to it. A willingness to accept incoming connections and a queue limit for incoming connections are specified with listen. Connections are accepted with accept. Okay. The behavior of the backlog argument of TCP sockets changed with Linux to Now it specifies the queue length of completely established sockets waiting to be accepted instead of the number of incomplete connection requests. The maximum length of the queue of incomplete sockets can be set using When sync cookies are enabled, there is no local maximum length and this setting is ignored. Okay. In the backlog argument, if the backlog argument is greater than the value in SOMaxCon, then it is silently kept so that to that value. Since Linux 5.4, the default in this file is 4096. In earlier kernels, the default value is 128. Before Linux, the Linux was hard-coded to was a hard-coded value with the value of blah blah blah. So now I'm on TCP server client example C. I think they are using SOMaxCon. Client, listen, 5. Okay, 5. Why 5? Because whatever. Okay, strange stuff. But so this is the maximum number of connections we should be able to process in the server. Okay, so let's make a version of the server that can be used, and then let's try to make 1000 connections, because now it should be possible. We don't have this. Yes, this on progress, except failed. So this should be fine. We can remove this one and this one as well. Okay, now, yeah, fine. Non-blocking set, 60, fine. Cool. Break, not in within statement. Yeah. Okay. Return pending. Okay. So 10 connections. Fine. Let's do 20 connections. Let's increase by the power of 2. So let's see, and the whole purpose is that we have the cycle time on the server, and we want to check how the connections affect the cycle time. Okay, so 10 connections, start, 10 connections. Now we stop. We should have 0 on both sides. Yes, 0 and 0, fine. And now we see the listening socket has created 10, nothing in the queue on the user space queue. Fine. Now we create 20 connections. 20 connections. Fine. We stop 20. 0 on this side, 0 on this side. We create 40 connections. Start. Okay. Okay. At least a server and client is server and client are telling the same. Okay, let's stop. We should get an error somehow, I think. No. Whatever. Let's stop. Let's make 80. $78. I don't know. Okay, at least it is the same. 160. And let's make it programmer like 128. Yes, I understand. Because now we have the same issue. Now we have the same issue. What? Closed already? Connection error occurred. Receive failed. Okay, let's check again. If we can 60, I think it was. Silently kept. So 1096. 4096. No, that's not the number. That's not the number. 2000. I know 2000 and this one times 2 times 2. That's hexadecimal. Okay, 2021 times 2 times 2. Almost. Yeah. Yes, now it looks fine. Okay. Let's check if this has affected something. 128 connections. Start. At least the same, yes. At least the same. And we have yes, we have for 122 connections, we have 10 milliseconds already. This is milliseconds, I think. No. Cycle time. Oh, I have to add. I have to add the unit. the unit in at which a main, it's measured in the main, and we have cycle diff in 10 microseconds. Yes, diff in 10 microseconds. We have a sum, and the sum in the cycle is in milliseconds, I think, because the average divided by 100 is double. Yes, this is in milliseconds. I should do ms cycle, ms cycle. If you need think about it, I think name it right. There it is. Yeah. So the names are very important. And now we see that it is quite cool already. We make something else now. We have the message dispatching process. The message dispatching process is no, the game supervising process. The game supervising process is showing us the cycle time in milliseconds. And then we remove one tab, hopefully. It's fine. Yes, perfect. Cycle time in milliseconds. So this is 1 millisecond. How does the process communicate with each other? The inter-process communication, yeah. So actually, if you the whole system I'm using is I've developed in 2018, and I'm using it since, because it may look strange, but I'm very satisfied. Although I had this bug today, it's still very cool to use it, I think, personally. github.com, you can know orientation programming. It's called the processing core. You can check it out if you want. And I have created some tutorials how you can use it. Essentially, this thing is creating a base requirement for your software structure, and this software structure is a recursive structure. Means everything is polled all the time. So as the base scheduling is made in the main, and essentially it's doing 16 bursts of the entire tree. The tree is executed here. This is the application, and the tree of the entire application is updated 16 times for every cycle, and then we are sleeping 2 milliseconds. This is the base scheduler for all the base processes, and this structure is this system is defining a base structure like in LaTeX or something like that, and the interprocess communication is not defined essentially. If we create, for example, if we create a new process, I have a template, CPP processing, let's call it test, then it's called testing, and this is the content of the file. Come on, open it. So this is the content of the file. Essentially, you only have one process function, nothing more. You always have one process function, and it's like the loop function in the Arduino. And And the cool thing, it's recursive. You always have a process function. It's no matter in a low level or high level, it's always the same. It's just a function that is executed cyclically. And I think this has a lot of advantages if you do it like that. Yeah, like a game loop, But the cool thing is you're not leaving the game loop at any stage. Everything is a game loop. And